very happy to have Danny Weiss here today. Danny is from McGill University, but he's spending this year in Weizmann. The title is Snapshots in Group Theory. So today it's here. The next two lectures are in the Science and Education building on the 6th floor. Tomorrow it's at 2 p.m. and the next day at 11, the final lecture series. And I should thank the Center for Scientific Computation and the Faculty of Natural Sciences for helping to fund this event. So yeah, the overall title is Snapshots in Group Theory, and today it's the cubical route to understanding groups. Maybe we can all welcome.
Yay! Okay, so that's not quite right. So this is a little outdated. I'm going to. This is more a snapshot of my life. This talk. The other two talks will be sort of, I hope, more traditional lectures. I'm most delighted to be here. I don't think I've visited the math department here, although I know a lot of the mathematicians here. Some are old friends, some are new friends. Haifa is a city that I've slept in many times because my wife's grandparents were here, so I was put to sleep in an old age home in the afternoon by people that spoke Hungarian that I'm not really convinced is an actual language. So it's great to be here. So I'm going to tell you sort of a plan, a scheme for understanding a group. It's not going to be so clear, and then I'll explain. I'll tell you the steps. Did I destroy something now? Yep. Didn't take very long. Okay. I won't step on it again. So the plan is firstly to find a bunch of codimension 1 subgroups. Okay, those are groups that cut. Those are subgroups that cut the group in half. Okay, the codimension 1 subgroups, and then you obtain an action of G on a cat0 cube complex. Okay, it's a very Haifa topic, in fact. And then if the codimension 1 subgroups are nice enough, then the group will act nicely. And then if you are lucky enough or thoughtful enough to find a finite index subgroup where the quotient complex is very organized, that's what we call a special cube complex. And if you manage to do all of that, then you succeed in finding an embedding of your finite index subgroup in what's called a right-angled Artin group. And that's considered a success. You've understood the group. Okay, so this should make you feel like if you haven't seen this discussion before, I've been talking about this for 20 years or so. It should make you feel like you're not going to understand my talk, but you will. So let's get on it. I tried to illustrate some of the steps at the bottom. It's not important. So let's do what we need to do, which is to tell you what cube complexes are. So cubes, a cube is one of these, right? It's just a product of intervals, and cubes have subcubes, right? So you can see a 2 cube. We call those squares, and there's a 0 cube over there, highlighted in red. And a cube complex is built from cubes by gluing the cubes together along subcubes. It's kind of similar to a simplicial complex, right? But instead of building from simplices, we're building from cubes. And so here's an example of a cube complex over here, right? You could see the rules of the game for me is if you think you see a cube, there's a cube. Okay, so there's a 3 cube, you see it. Here's a 2 cube, I stretched it out. Okay? Now, I need to tell you what non-positively curved cube complex is. So to that, I need to say what a flag complex is. So a flag complex is a simplicial complex with the property that whenever n plus 1 vertices span an n simplex, that's actually the same thing as those vertices being pairwise adjacent. So let me, it took me a while to learn that definition actually. Here's how I think about it. You, you look at your simplicial complex and you just think about its one skeleton, just its one skeleton, right? So you're looking just at a graph. And then you say to yourself, anytime that I see the one skeleton of a simplex, the whole simplex is there. Okay? If it's true that a simplex is there whenever its one skeleton is there, that's called a flag complex. It's a very sweet definition because it means that you have control over high-dimensional stuff just with one-dimensional information. Okay, and you could think about the, you could now think about it easily. So, so a flag complex is a very nice simplicial complex. It's one where the simplices aren't missing; they're there. Here's two examples of flag complexes. This is an octahedron. It's well known. Okay, no higher simplices, just it's two-dimensional. And here's a graph which is a flag complex. So a graph is a flag complex if there aren't any. A one-dimensional simplicial complex is a flag complex if there aren't any 3 cycles, or 2 cycles, or 1 cycles. Okay. Now, what's the connection to cube complexes? Well, if you look at a 0 cube and you put your eye where that 0 cube is and you look out, then what you see is corners of cubes. You see the ends of cubes, right? So if you're looking into a 1 simplex, you just see a point. And if you're looking into a square, if your eye is right here and you're looking out into a square, then you see just an edge, right? You see this, right? If your eye is right over there. And if you're looking into a 3 cube, right? Imagine your eye is at the corner right over there, and you're looking into the 3 cube. What you see is a 2 simplex of directions, right? So the link.
Here, the original complex is a cube complex, and what you obtain is a simplicial complex in general.
Exactly. So if you're at a 0 cube in this cube complex, right, and you look outwards, then you see what's called the link of that 0 cube. And you can also think of it, instead of visually, you could kind of pretend that there was a metric, and this red simplicial complex that you're seeing, you can also think of it as a kind of epsilon sphere around this 0 cube. Okay? That's kind of natural, I think, for everybody here. So that's the link. And the way we define a non-positively curved cube complex is quite simple. We simply require that the link of every 0 cube in your cube complex X is a flag complex. That's all. So now you all know what non-positively curved cube complexes are. It's a little bit, well, it's a very simple combinatorial way of thinking about curvature. It's not so clear why this is the right definition, or why the words curvature are even being used over here, but it's the right definition. Maybe for a little bit of intuition, we could stop and think about a surface, right? And we might regard these as pictures that we would expect to see on a sphere, in a flat plane, or in a hyperbolic plane that was tiled by squares. Okay, and so we start to see, hey, yeah, this is positive curvature, maybe this is flat, 0 curvature. Here we have negative curvature. And if you think of the links, well, for the zero curvature and the negative curvature case, you have a 4 cycle and a 5 cycle as the link. And those are flag complexes. But for the positive curvature case, you have a 3 cycle as the link. It's missing, there's no 3 cube over here. And it's missing the 2 simplex. Okay? And this is not going to be a non-positively curved cube complex. This is just a 2-dimensional object. These are non-positively curved cube complexes. All right, so I mentioned already that in dimension 2, your cube complex, we might call it a square complex, it's built from squares, it's non-positively curved if all of its links are graphs with girth at least 4. The girth is the smallest cycle that you have in your graph. And actually, so for some quick examples, any graph is non-positively curved, right? Think about what the links are. They're not very interesting. There aren't any edges, right? The links are just sets of vertices. Any closed surface, that's fun to do if you haven't seen this before, any closed surface except for a sphere or projective plane is homeomorphic to a non-positively curved square complex in many ways. And if you take 2 non-positively curved cube complexes, then their product is again a cube complex. You have to think about why, right? Products of cubes are cubes. And their product is again non-positively curved. And it's fun to think about why that would be. All right, so we already know what a non-positively curved cube complex is. Now I'm going to tell you what a right-angled Artin group is. So if you have a graph gamma, then there's an associated group, and the group is given by a very easy presentation. There's a vertex, the generators correspond to the vertices of your graph, and 2 adjacent vertices will give you commuting generators. So this is the presentation. So you have to stop and sort of decode the meaning, right? If you take this graph over here, the first one, then we've got 3 vertices, and any 2 of them are adjacent. So 3 generators, any 2 of them commute. So you get z times z times z. It's z to the 3rd. And if you look at this example over here, this is a complete bipartite graph with 2 vertices on the left and 3 vertices on the right. So these 2 generators commute with those 3 generators. So you get a free group of rank 2 product with a free group of rank 3. And here's another example, which is a very pretty example. If you take these 4 vertices, right, first one commutes with the second commutes with the third commutes with the fourth, you get a presentation. You now know the recipe. And it turns out that this one is, it's the fundamental group of the complement of this chain of 4 circles, right? I know someone's teaching knot theory this semester, so it's fun to work out the presentation. Okay. Ask.
Is it possible to get a surface group, like out of a certain graph?
That's an excellent question. The answer is only the torus. The torus is the only example that you can get like this, and so let's think about why. Any 2 generators commute. So if you had 2 vertices that were joined by an edge, looks like there'd be a z times z subgroup inside, and so it's probably going to be a torus if it's a torus. So now you're happy. Okay. So in fact, whenever you have, here's a crazy graph that I drew over here, and here's all of its generators and relators. Whenever you have a graph, gamma, the right-angled Artin group associated to gamma is the fundamental group of a non-positively curved cube complex that we call the Salvetti complex. And I illustrated over here, but I'll just tell you very quickly how to do it. It's rather simple. you see, we started off by taking, so this is a good example, right? Over here, A, B, C, D. Here are the 4 generators. We added 4 commutation rules, right? You could think of those as being adding 2-dimensional tori, right? So we started off with what's called the standard 2 complex of the presentation, right? We took a 0 cube. We added a 1 cube for each generator. We added a square, a 2 cube for each relator, right? So far we have 4 squares because there are 4 edges over here. And then the rule is that you add an n torus in the most obvious way for every collection of n pairwise commuting generators. Okay, so that's a lot, but it's not too much. So over here, A, B, and C commute with each other, right? A commutes with B commutes with C, and A commutes with C. That's 3 pairwise commuting generators. So I'm going to be adding a 3 torus to make this square complex, right, which corresponded to the presentation of the right-angled Artin group. That's a 2-dimensional cube complex, but it's not non-positively curved yet. I want to add more to it. I'm going to add a 3 cube, and the 3 cube corresponds to these pairwise commuting 3 generators, A, B, and C, right? And it's the most obvious 3-dimensional torus that you know, right? You take a 3 cube and you identify the top and the bottom, the left and the right, the front and the back, and those correspond, if you label things properly, those correspond to squares that are already there, right? And you glue it on. You add it. And you do this for any collection of pairwise commuting generators that you see, for any collection of pairwise adjacent vertices that you see in your graph, you will add a torus. You'll add an n torus in the form of an n cube. And when you do that, it's not very difficult to see that the non-positive curvature condition that I told you about before is satisfied. Okay, so every right-angled Artin group is the fundamental group of a non-positively curved cube complex, one with a very sweet description.
So there's only 1 0 cube, and all the corners of all the cubes in dimension glued to this one.
Exactly, and so you sound like you would enjoy working out what the link is, right? From your voice, I can tell, right? Yeah, and there's usually, and anytime you give a colloquium, there's one of these guys. So I found them, and it was fun to try to see what the link looks like from the initial information that I gave you here. And in fact, for this particular example, is a great example to work through. Okay. So we now know right-angled Artin groups, we know non-positively curved cube complexes, and now cat zero cube complexes. Now, Haifa is the land of cat zero cube complexes, in fact, okay? Because my colleague, my collaborator, Micha Sagiv, is here. Yael started off doing cat zero cube complexes a long time ago before she started doing outer space. Boo for outer space. Nir Lazarovich, your colleague, I don't know how far are we, how many kilometers are we away? Does anybody know? 5, yeah, but it feels like 50 in Haifa. I know already how that works. So what is a cat zero cube complex? These are simply connected, non-positively curved cube complexes. That's all. So you know what a non-positively curved cube complex is? It's a complex built from cubes, and the links are flag complexes. It's cat zero. That means that it's simply connected non-positively curved cube complexes. But what are they really? They're really generalized trees. They're high-dimensional trees. That's what they are. That's how they behave. That's how we view them. That's how we think about them. That's why they're useful. So I've drawn one which I think is a a featured favorite object in math, right? It's a hyperbolic plane cut up into two-dimensional cubes, right? And when you have this term cat zero, it's a Gromov joke. Gromov introduced cat zero cube complexes and kind of popularized them as examples to illustrate cat zero spaces. Cat zero, which is a term that kind of put you off maybe, it just the names Kartan, Alexandrov, Topoganov are here. That's the cat. Zero means less than or equal to zero. This means non-positively curved and simply connected. And cat zero, a cat zero metric space is cat zero cube complexes are called that because they have cat zero metrics. And a cat zero metric, they have cat zero metrics where all of the cubes are isometric to standard Euclidean cubes. And a cat zero metric, which you're not going to have to know, but I'll mention it over here because just so you understand what's going on. A cat zero metric is a metric space where any 2 points are connected by a geodesic, and where for any 3 points like A, B, and C, if you look at the geodesic triangle, or if you look at any geodesic triangle with vertices at those 3 points, it's at least as thin as a comparison Euclidean triangle. So you take a Euclidean triangle that has the same side lengths. It's a fun puzzle for students of any age, that there exists a Euclidean triangle with the same side lengths, no matter what. And you take points in your triangle, like P and Q, and you look at the corresponding points and the corresponding positions in your Euclidean triangle that you're going to compare it to. And what you want is that the distance between P and Q is less than or equal to the distance in the Euclidean plane between their corresponding points P prime and Q prime. And if that inequality, famous from Riemannian geometry, people who are looking at global conditions a long time ago, if that inequality is satisfied, then the cat zero, then this geodesic metric space is a so-called cat zero space. And this abstraction and generalization of things that people were studying and using, calculus and integrals and who knows what, it all of a sudden became available to those of us who are not integral people, but like to know what's going on, right? And it all really boils down to this amazing inequality. It's remarkable. So Gromov popularized that too, and there weren't a lot of examples in high dimensions, and he said, okay, you can use cat zero cube complexes, and he gave a condition which is not a little bit different from the condition that I showed you, to recognize a cat zero cube complex. And those were like 2 lines in one of his essays someplace, and he moved on to other stuff. And Gromov is a genius, and there's no way in the world that he had the vision of how significant these cube complexes were, even for the field that he was founding, geometric group theory. It's impossible that he understood. But he's a good guesser. He's good. He has good instinct, and that's why he has so many followers. And okay, let me continue the story. So I said that I told you about the metric, and now you know why the word cat zero is there. But it's not what makes cat zero cube complexes tick. It's not what gives them their behavior, this metric. It's not quite. The thing that gives them their behavior are what are called hyperplanes. So let me tell you a little bit about hyperplanes. A mid-cube, and I'm following my friend Micha Sagiv for a lot of this talk. I was working just in 2 dimensions, a couple of years behind him. He's a couple of years ahead of me. And he was doing his important PhD thesis, and I was working in 2 dimensions, doing whatever silly things that I was doing. And then I found out that he was, what he did, had a very big impact on me, and I was able to move to higher dimensions. So let me tell you a little more. So a mid-cube in a cube is one of these kind of cut it right in half sub things. So in terms of the coordinates that I gave you, it's the subspace that you obtain by restricting one coordinate to 0. So start with a square. A 2 cube has a red mid-cube and it has a blue mid-cube, right? And a 3 cube has 3 mid-cubes. You could see them, right? The 3 mid-cubes. I've drawn only one of them. Right? A 1 cube has 1 mid-cube, just one little point right over there. Right? A 0 cube doesn't have mid-cube. A hyperplane is a connected subspace that intersects each cube in a single mid-cube, or it doesn't intersect it at all. So in this kind of duck dinosaur looking cube complex, you can see that there's a blue hyperplane. It follows the rules that I gave you. See that blue hyperplane? See, every time this blue subspace touches a cube, it doesn't just touch it in a little part of it, it cuts right through it as a mid-cube, okay? And, so you can see that here's a red hyperplane as well. It follows that rule that whenever it intersects a cube, it intersects it in exactly a mid-cube. And crucial point over here is, let me emphasize more. I think that what you should be doing now is you should be imagining starting someplace, like right over here. You start right here, start in this mid-cube right here, and then just follow your eyes and say, according to the rules, how you have to continue in order to get a hyperplane. Because it just, boom, it just goes. It's forced to go in a certain way. And it doesn't come back and crash into itself. Okay? And it kind of locally separates, right? It locally separates because it kind of has the hyperplane has a kind of product neighborhood, right? Exactly by the way we're describing it. So that manifests itself as follows. Every mid-cube actually lies in a hyperplane, in a unique hyperplane. Just you see how it has to be unique. Question is, does it really exist? Does it come back and crash into itself? No. The non-positive curvature prevents that. The hyperplane separates the cat zero cube complex into 2 parts called half spaces, if you'd like. The part on one side, the part on the other side. And hyperplanes themselves are cat zero cube complexes. Okay? It's a fun exercise, I guess. And it's these hyperplanes that give a cat zero cube complex its nature, its properties. And these hyperplanes generalize the role of edges in a tree. So what makes a tree into a tree? It's a connected graph with the property that every edge separates it. And that would be one way of saying what a tree is, and that's very useful if you're thinking of trying to do things with trees, just to know that that edge, there's the stuff on the one side of the edge, stuff on the other side of it. It's very simple-minded. And we have that simple-minded power now as well in higher dimensions, right? So we have these higher dimensional objects, maybe 730 dimensions, and they have the same game. They have these cut in half in different ways, okay? With the hyperplanes. And well, here's another well-known cube complex. It's just a plane cut up into squares. Not so interesting. The example that I showed you before of the hyperbolic plane broken up into squares is more interesting. And then you could see here's a red hyperplane inside. And you can imagine many other hyperplanes, and they kind of look like geodesics in hyperbolic geometry, right? Okay, so now I told you that there would be organized cube complexes. This is a topic with my friend Fredrik Haglund. And we call them special cube complexes, sort of in a giddy spirit a few minutes after we started playing the game. But we should have called them organized cube complexes. So first of all, you need to know what an immersed hyperplane is. So, and I think you'll be very quick to catch on. So if you have not a cat zero cube complex, but a non-positively curved cube complex, and you play the same game I was telling you before, you start at a mid-cube somewhere inside, and then you just kind of wander off to the next mid-cube in nearby cubes, and you keep on wandering around. Then you get something which might come back and crash into itself and pass through itself. But you can imagine it kind of living outside and immersing in. And that is an immersed hyperplane instead of a hyperplane, right? We can give fancy definitions, fancy rigorous definitions, but I think that's the right way to think about it. So I've illustrated an example over here, right? Here's a non-positively curved cube complex. And I started maybe with this one mid-cube right over here. And then I continued, and I got this object, which you can imagine living outside and then mapping in, right? If you wanted to be very rigorous and severe, what you could do is you could take all of the mid-cubes of all of the cubes in this cube complex, and then make a rule of when two of them should get glued together, a fairly obvious rule, and then you'd have a collection of immersed hyperplanes that together map in, right? And we're looking at one component in this collection. But I'd say stay with this more down-to-earth, start someplace and continue, you get this immersed subspace. And using these immersed hyperplanes, we define what we call special, and it's a strange definition. No hyperplane self-crosses. So immediately I got you into allowing yourself to have this immersed thing that maybe crashes into itself, and then I say, no, I will not allow it. Okay? Hyperplanes, these immersed hyperplanes, they have to be actual hyperplanes. They can't self-cross. They have to have that same property that they're connected subspaces that intersect any cube, if they do intersect it, in exactly one mid-cube. So that makes things simpler. And I've illustrated the things that are not allowed over here. First, second, third, and fourth. No hyperplane self-crosses. This is not allowed. No hyperplane is one-sided. So in the picture of the cat zero cube complex, as I told you, there's like there's a left side and there's a right side. I want that same behavior, right? And I've drawn for you a famous example of something that we love, but I'm not allowing. Okay? This is important to us because it's one of the ways that we can tell our friends who are not mathematicians that we're doing something interesting. Okay? So this is not allowed. There has to be a consistent right side, left side. No hyperplane self-osculates. It's a little bit of a harder definition. So not only can hyperplanes are not allowed to crash into themselves, they can't even come close to themselves. Kind of kiss themselves is the word osculate that I learned in the footnotes in some calculus book 30 years ago. And I never used it until I met my wife. Okay? The fourth is no pair of hyperplanes interosculate. That's a hard definition. So that says if two hyperplanes, like this red one and the purple one, if they cross each other in one spot, they can't just come right next to each other and osculate in another spot. They actually have to cross again. So I didn't draw it here, but if this were what would be allowed would be, okay, they come close to each other, there must be a square. So you can imagine adding a square right over here, and then they enter that square and cross each other inside of that square. That's allowed. Okay? The way Frederic has a brilliant memory, I have a terrible memory. I could never remember that, and so I think I said, crossing pair has a square. I can remember silly things like that. So anyway, these are special cube complexes, and somehow we dreamed this definition with another motive, but we quickly, oh, and I gave an example. This is a very strange example. Any subcomplex of the product of two graphs is special. I already told you that a graph is a non-positively curved cube complex, and the product of two non-positively curved cube complexes is a non-positively curved cube complex. So the product of two graphs is a non-positively curved cube complex. And if you take a subcomplex of such of that, it's actually going to be special. You can even convince yourself quickly. And this is a very strange example because I think that, well, I know that an extraordinary array of groups that arise both in geometry topology and in combinatorial group theory are actually fundamental groups of such subcomplexes, or at least they have finite index subgroups which are fundamental groups of such subcomplexes. This is a crazy thing. It's a strange thing. So it is disturbing, in fact, if you picked apart what I'm telling you, and I really mean it. I think most of the groups that anybody here has thought about, say if you're doing knot theory, there are almost all of them have finite index subgroups that are fundamental groups of such things. Okay, it's strange. So we noticed quickly, we were cooking up this definition for another reason. We noticed quickly that X is a non-positively curved cube complex. X is special if and only if it admits a local isometry to the Salvetti complex of a right-angled Artin group. So what does this mean? So I guess local isometry has a very simple combinatorial definition I won't give you. Maybe you already accepted that there's a locally cat zero, that there's a cat zero metric, and a local isometry really means that you have metrics on these two cube complexes, and the map, this combinatorial map is actually a local isometry between these with these local metrics in mind. But there's a very sweet combinatorial definition as well. In any case, what it meant was that somehow there's this bridge from cube complexes to these right-angled Artin groups through this notion of a special cube complex, of a cube complex whose hyperplanes, whose immersed hyperplanes are very organized. And local isometries, just as in the Riemannian case, they induce pi1 injections, right? Because in the universal cover, a map between local isometries becomes an isometry, in fact. It becomes a convex embedding when you look at the map between the universal covers. So it becomes a pi1 injection. So this really is a good bridge somehow from fundamental groups of certain cube complexes to right-angled Artin groups, to get you subgroups of right-angled Artin groups. And this bridge turns out to be very powerful, because it could take us from a combinatorial, sort of more topological, maybe some topological situation that we're in. We can combinatorialize it, and then we could push further and get some group theoretic information. Simple things are good. This is very simple, actually. This is not. I'm telling you something very simple. I'm not sketching why it's true. But this is a very easy theorem, in fact. G is special. A group is special. Why not? If it's the fundamental group of a special cube complex. And it turns out to be the same thing, based more or less on what I've just told you. A group is special if it's a subgroup of a right-angled Artin group. And well, special cube complexes, you could think of them as high-dimensional graphs, and a special group, you could think of it as a kind of relaxed version of a free group, in fact. What is this a picture of? Here, just to sort of reassure you a little bit, here is a special cube complex. It has two 3 cubes and 4 extra 2 cubes. And this is the associated right-angled Artin group that this cube complex maps to its Salvetti complex by a local isometry. And the relationship between them is very natural. I'll spill the beans and tell you the vertices of this graph are in one-to-one correspondence with the hyperplanes of your cube complex, and two vertices are adjacent if the hyperplanes cross. That's it. And the map turns out to be very natural. Okay. Now I will quickly tell you about wall spaces and Sagiv's dual cube complexes. So a wall space, which is a notion which was actually invented by Frederic Paulin and Frederic Haglund. A wall space is a space S together with a bunch of walls. Okay? And each wall is really just a partition. It's really a wall space. Haglund and the two Frederics are very abstract thinkers. For them, when they expressed this, when they abstracted this notion, it was really a set together with a collection of partitions of the set with certain properties. But I'm not going to do that to us. We'll be very concrete about it. You have this set, which is like this oval thing over here, and then a bunch of walls. Each of these dotted lines is a wall, and the wall separates things on the one side and partitions things on the one side of the wall from the things on the other side of the wall. Okay? So I don't know how many walls I have over here. It looks like about 12 or so, right? Here's another simpler wall space. Here's a more complicated wall space with, 3 families of walls. Vertical and 2 diagonal families of walls. And Sagiv, who didn't have the word wall space because they were working separately, he created a notion of a dual to a wall space, and he got a cat-zero cube complex. And it's a dual which generalizes the dual that you know already. Okay, so let's start in this situation that you know.
You mean the polar dual?
No. I've used polar duals for cube complexes, but no, I don't mean. Okay. I don't think this is the polar dual. Okay. Let's start in the middle because it's easier. Okay? I have this sort of tiling. Think of it as a tiling. If you have a tiling of a surface, then you know that there's a dual. You take a vertex, 0 cube, for every region, and when two regions share a common border, then you connect them with a 1 cube, right? And when a bunch of regions sort of travel around some point, then you add a 2 cube. This is the dual, right? This is a dual that, it's an exciting dual. When we first learned about it, you all have seen this before. The question is when, at what point were you 15, 17, 19, or 21? Okay? And here was a wall space, and here's its dual, a dual that you know already. And let's go backwards a little bit. You can play the same game with this wall space. It's a little bit less familiar, but it's easier. Do the same thing. There's a 0 cube for each region, and you get a 1 cube for regions that are facing each other along some border, that have a border. And Micha generalized this to any cat-zero cube complex, to any wall space, to create from a wall space a dual cat-zero cube complex. It's a beautiful construction. The way it goes is a little bit subtle, but very simple. A 0 cube, I like to think about it in the following way. A 0 cube is a kind of orientation on each wall. So for any wall, here, let's look at this picture over here. For any wall, I imagine that there's kind of a red normal vector, and you could decide if the red normal vector is going to point to one side or if it's going to point to the other side. So a zero cube is a choice of an orientation. It's a choice of a normal vector for every wall in the whole wall space, right? So see, I've chosen a red normal vector for every wall over here. That could be a zero cube, okay? It's more abstract than putting a point in the middle of a region, isn't it? But that's okay. And there's just a small fine print to that definition. We need to require that you don't have any two normal vectors pointing away from each other. Not allowed. Okay, so a fancy way of saying that is that the chosen half space, you're choosing one half space for each wall. You're choosing one of its two half spaces, and you require that any two chosen half spaces, right? A zero cube is a collection of chosen half spaces, one for each wall. Any two chosen half spaces have to intersect each other. That's a little bit more correct.
They all intersect.
Huh?
If they pairwise, they all intersect.
If they all pairwise intersect, then you're happy. Okay? And now, maybe there's one more fine point, is that you only funnily many walls. So let me say it like this. Pick a point, S, in your wall space, in your set of points in your wall space, and you require that all but finitely many walls are pointed towards it. Okay, so you're not allowed an infinite family of walls pointing away from the same place. Okay, so let me quickly spill the beans. You now know what a zero cube is. You add a one cube whenever two zero cubes disagree on exactly one wall, right? A zero cube, it's a choice of orientation for every wall. If they disagree on exactly one wall, you join them by a one cube. And then you add higher cubes whenever you see their one skeleton. So whenever you see a 4 cycle, you add a 2 cube. Now whenever you see the 2 skeleton of a 3 cube, you add it. And that's the whole definition. Okay, so that's Sagiv's dual cube complex. Now I'm going to accelerate because I have been too nice to everybody here. And I'm not going to be able to get to the harder things over here, but that's okay. So everybody knows what was happening at the Technion and before Micha got to the Technion a long time ago. Calligraphs, we know, if you have a group, you can turn it into a geometric object by having a vertex for every element, and if you've chosen generators, you join G times a generator to the product. Right, that's you get a calligraph in that way, and then there's what we call hyperbolicity. So a group is hyperbolic. Well, so the calligraph, there's now a path metric, and there are geodesics in this calligraph, and you can look at triangles that are formed whose sides are all geodesics, and there's Gromov invented hyperbolic groups. There's this calligraph is called delta hyperbolic. If any triangle is delta thin in the sense that any geodesic triangle has the property that each side lies in the delta neighborhood of the other two sides within the calligraph. And there's also a notion of a quasi-convex subgroup, which means a subgroup which is nearly convex. So any geodesic joining 2 points in this subgroup, any geodesic in the calligraph joining 2 points in the subgroup, lies in some uniform neighborhood. Okay, that's a quasi-convex subgroup. Yes?
The calligraph is like just a subspace of Rn with the standard metric.
No, better not.
What does it mean, the delta neighborhood?
So the calligraph, we define a path metric, right? And for any 2 points, you look at the minimal number of steps. The distance between 2 points is the minimal number of steps, meaning edges, to be able to travel from one vertex to the other vertex. That gives you a metric, and so we're taking we're taking neighborhoods in just that metric space, not embedding it in anything. Okay, so there's actually also a boundary. There's Gromov's boundary for a hyperbolic group. You kind of, you look at the set of all geodesic rays that start someplace, and that gives you actually extra points at infinity. You have to, and there's a way to topologize that. That's very natural. For a free group, maybe the Cayley graph is a tree if you choose good generators, and then the boundary ends up being a Cantor set. And once you see that, you can get sucked into some topic in mathematics, and you end up computing fractal dimensions and who knows what. Okay, it's an amazing business. All right, so to quickly tell you, Micha's PhD thesis is so important for me. I need to tell you a little more about it. Here it is. If you take, so what is a codimension 1 subgroup? I told you earlier, codimension 1 subgroup, it's a subgroup that cuts the group in half. It cuts the Cayley graph in half, right? And what that means roughly is if you look at the Cayley graph and you look at this subgroup inside, and you kind of take a neighborhood of the subgroup, and when you take the neighborhood of the subgroup and remove that neighborhood, you're left with two components. Okay? This is a white lie. The actual definition is a little bit different, but that's close enough so that if you went and thought about it, you'd know what the definition is. And so in fact, any Zn in Zn plus 1 is a codimension 1 subgroup. You kind of, here's just a Z1 inside of Z2, but if you take a genus 2 surface and you take a pi1 injective immersed circle, then you get a cyclic subgroup of a surface group, and that's also going to be codimension 1. And if you look in the universal cover, well, the universal cover of this surface is a hyperbolic plane, might as well. It roughly looks the same thing as the Cayley graph, right? And I'm not drawing it that way. And you'd get the cyclic subgroup would be some nice periodic liney thing in the Cayley graph that looks more or less like the hyperbolic plane. And this codimension 1 subgroup would more or less look like a bunch of points along this line. And if you took a neighborhood of it, it would cut the hyperbolic plane in half. Same kind of idea. And what Sagiv did was he said, okay, if I have a codimension 1 subgroup, I get a wall from this codimension 1 subgroup. If you kind of imagine it, thickening it up slightly, there's the stuff on one side and the stuff on the other side. So a codimension 1 subgroup gives you a wall. And if you look at all of its translates, well, now you have a wall space, many walls. And of course, the wall space has a dual cube complex. And the group is acting when it acts on all of these translates of your codimension 1 subgroup. It's permuting around all of your walls. The group is acting on the wall space, and so it's easy to believe that the group is now acting on the associated dual cube complex. That was Sagiv around 1995. And here's a simple example of just to have in mind of you surface group, you get a wall, one of these black walls over here, and now the group is acting on that, and you have now the group is acting on the dual cube complex, right? So you got a wall, you look at all of its translates, you get the group acting on a cube complex. So now this is the vehicle that we will use to get us from a group to a cube complex. You have a group, you find a codimension 1 subgroup if you're lucky enough. That gives you a wall space. The group now acts on the dual cube complex. Now we want to understand our groups, so we want to get it to be organized. We want it to be special, okay? But first, let's stop for a moment. Kahn and Markovich did something amazing that you might have heard of. it's about 2012 now, they showed that if you have a closed hyperbolic three-manifold, then there are many pi1 injective immersed closed surfaces inside, right? And a two-dimensional surface inside of a three-dimensional manifold feels codimension 1, and it is actually, if it's pi1 injective. So they found codimension 1 subgroups, in fact, quasi-convex codimension 1 subgroups inside of your hyperbolic three-manifold group, right? And actually, there's a sweet condition that tells you, in terms of boundaries, that tells you that if for any 2 points in the boundary that I told you about, if for any 2 points in the boundary, you can find a codimension 1 subgroup whose boundary, right, which is going to be some wiggly thing at infinity, it's a boundary of, imagine the surface inside of the hyperbolic three-manifold. Imagine this kind of two-dimensional hyperbolic plane, wiggly hyperbolic plane inside of hyperbolic 3 space. For any 2 points on the 2-sphere at infinity, if you could find a quasi-convex codimension 1 surface, like Kahn and Markovich might give you, which separates those 2 points, if you can always find quasi-convex codimension 1 subgroups that separate points at infinity, then actually you can create an then you could choose finitely many codimension 1 subgroups, do the Sagiv's dual cube complex on the associated dual cube complex, and create an action on a cat zero cube complex. So from Kahn and Markovich, what we find is that any hyperbolic three-manifold, any closed hyperbolic three-manifold, its fundamental group is actually, its fundamental group acts freely over here and co-compactly on a cat zero cube complex. So actually your hyperbolic three-manifold turns out to be, its fundamental group turns out to be also the fundamental group of a 730-dimensional cube complex, a compact 730-dimensional cube complex, which maybe you turn something nice into something awful, you might think. And that's the way people were thinking about it in around 1985. But in fact, maybe not. Maybe you turned something nice into something that was more accessible, which turned out because it was more like just a simple graph. And I should say, so I just said that. Okay, let's never mind the cusp case. So now in like 4 minutes, I'll tell you about 10 years of my life. Okay, so you know the feeling. A group has a hierarchy if you can build it from trivial groups just by using what's called H&N extensions, which you might not have heard of, or amalgamated free products that you probably heard of, right? I think probably everybody here has heard of free products. You take 2 groups, you can form their free product, which is a new group. Right? It's kind of like the way you get a free group from combining 2 infinite cyclic groups. So there's a more general version. You can glue 2 groups together along a subgroup to get an amalgamated free product. And groups with a hierarchy are groups that you can kind of build in that fashion just by you just keep gluing more and more groups together along subgroups. And well, I showed that if you're careful about the subgroup that you're gluing along, if you make sure that the subgroup that you're gluing along is quasi-convex each time you do this, I showed that if you have a hyperbolic group with such a nice hierarchy, so if you could build your hyperbolic group just by using amalgamated products along quasi-convex subgroups, then your hyperbolic group is virtually special, which means that it is the fundamental group of a cube complex, which has a finite covering space. You can unwrap that cube complex to make it organized, to make it special.
That's the same as G having a finite index subgroup that's special.
It's exactly the same thing as saying that G is virtually means having a finite index subgroup, a subgroup of a right-angled Artin group. Kind of an amazing, an amazingly strange thing. Why should this be? Why should right-angled Artin groups be so greedy and suck up all of the other groups. Why should they, not all of them, but many, why should they all get pushed in there? And I did this in some other cases. I was very interested in the three-manifold case. I did it also for any hyperbolic three-manifold that has cusps. So these are the sort of not a closed hyperbolic three-manifold, but one that has sort of like little tori off at infinity. And I also did it for some other interesting cases, like if you have a group which is a one-related group with torsion. If you just take two generators, A and B, and you take the relator and you raise it to a power, then I showed that you can actually find codimension 1 subgroups, create this dual cube complex, pass to a subgroup of finite index, so that, or find the covering space of this cube complex where the hyperplanes are all organized, and you're inside of a right-angled Artin group. And right-angled Artin groups are very nice groups. They really are. Just a bunch of generators commute with each other. It seems so artificial. It seems like it shouldn't be useful for anything, huh?
But their subgroups aren't so nice.
Their subgroups are not so nice. They have many. They have more. It's more that they have many subgroups. Okay, they're just, it's like Rn. Rn is so easy, but its subspaces aren't so nice. Okay, that's the situation that we're in. And well, now you have in just 4 seconds. There was torture involved over here. There was, things that all of them are, several years of work and pain and suffering with unfortunate co-authors, and you don't need to know about it, so you can thank me for that. And the, special quotient theorem maybe is the one that turned out to be crucial over here, and I'll say on one leg that if you have a group that is special, right, or virtually special, and you have a subgroup inside of it that you don't like, then you can kill that subgroup, kill a finite index subgroup of it, really, and again, you're still special. So if you have something special, your group is special, there's a subgroup that you don't like, you can crush the subgroup, and then the resulting quotient is, again, virtually special. And that is a strange kind of Dane-filling theorem in this category, which is very powerful. And the end result, sort of completing and building on what I was doing, Egel, quite quickly after I had done whatever I just told you about, managed to prove this fact that if you have a compact, non-positively curved cube complex whose fundamental group is hyperbolic, then you can always unwrap it. You can always find the covering space of it, which is special. And this has immediate, immense consequences both to group theory and to three manifolds, consequences that I think that we are not yet fully, we haven't fully gotten used to it yet, and we haven't really unraveled what to make of it. But the strange situation now is that if you take a random group like this one over here, I know it's random because I did this on the bus. I put my fingers on the keyboard and I went with the bumps. Okay, the only thing not random about it is that there aren't any inverses, but otherwise I randomly generated this, and I could tell you that this, I know how to cubulate it because it's a small cancellation, and because of Egel proved this theorem, we now know that this strange random group, and in fact any random group with a fixed number of generators, it's virtually special. And so most groups from a certain viewpoint are living inside of these right-angled Artin groups after passing to a subgroup of finite index. A strange situation.
So is that
Talks over.
related to Gromov's theorem, where a randomly sampled group is?
It's very related. So the Gromov Gromov has a density model that you're alluding to, And what happens is that in Gromov's density model, at density more than a half, the group is finite. It's trivial probably, or a finite abelian group. At density less than a half, it's hyperbolic, right? That Gromov did that just in case he needed propaganda to support that hyperbolic groups were interesting, okay? But it became a game that people got interested in. And at density less than, so that in that model, what you do is you allow many relators instead of a fixed number of relators. You allow many relators, right? That's the way his density model. I'm not going to get into it, but what happens is that at density less than something, right? I proved that less than 1/6 with Jan Olivier, and other people have been pushing it to closer and closer to less than 1/4. I don't think we have it yet, but at a certain density, probably less than 1/4, all such groups are cubulated and therefore virtually special. On the other hand, Zhuk and others using Garland technology for property T showed that at density more than 2/3, the groups are always have, at density more than 1/3, the group has property T. And groups with property T, if you've heard of those unfortunately are never going to be cubulated. Okay, those are, I usually like to call them dead groups, but the people at Weizmann don't like it when I say that.
Of course not.
Okay. I am done. Thank you for listening to me. Yay.
Any questions? Okay, so just want to announce next talk is on the survey of the Khmer-Laudenbach conjecture. And
Right.
do we have to understand what you said today to understand the next talk? Or it's
It
gonna
will be completely unrelated.
So
Be
that's
totally fresh start and totally, right, that's the way to do it.
Join us for lunch. You're welcome.
Let's thank Danny again.
Thank you for not falling asleep.
See you tomorrow at 2.